So you are welcome back to the uh, class, the linear analysis class. So today we want to look at the continuation of convergent sequence. So where we stopped in our last class, we are talking about the relationship between a convergent sequence and a bounded sequence. Okay, we have been able to say that every convergent sequence is a bounded sequence, whereas the converse is not true. Okay, so later we'll be talking about uh, we'll be given the reason why uh, when we impose additional condition, we can now say every binary sequence can be a convergent sequence. Okay, but for now, let us look at another concept of a of convergent sequence. So when we say a sequence is convergent to a particular limit, okay, we want to see a theorem that says such a limit is unique. Okay, so we refer to that as uniqueness of limit. So we stated this as a theorem, uniqueness of limit. So it says that if a sequence Xn converges to a limit L, then the limit is unique. So let's have the proof for that. And we are using the notion of contradiction. That is, we want to prove this by proof with a contradiction. And how do we contradict this statement? Is to assume that the limit L is not unique. Okay, so say it has two limits L1 and L2. So by definition, we are referring to the definition of convergence. By definition, so that will be given number epsilon greater than 0. There exists a particular length called the n of epsilon such that Xn so we'll have two n1 of two n of epsilon. We call the first one n1 of epsilon and n2 of epsilon, such that Xn minus L1 is less than epsilon for the first n greater than the n1 of epsilon, and Xn minus L2 is less than epsilon for n greater than n2 of epsilon. So respectively, okay, so now we want to see when we have two limits. Of course, the basic assumption there is that N1 and L2 are not the same. Okay? So let us see the difference based on the definition we have here. Let us see the difference between the two limits to see whether truly the limits are the same or not. Okay, so if the two limits are the same, this means that this contradicts the statement that says there are two limits. Okay, so if they are the same, okay, this agree with the theorem. Okay, so now let n of epsilon be the maximum of n1 of epsilon n2 of epsilon. So then we want to see the difference between the two limits. Okay, the condition we have imposed earlier is that this is not equal to 0. Okay, we want to see whether the difference together with these conditions, whether it will be so or not. Okay, so let's see. So this is equal to n1 minus xn plus xn minus n2. Okay, so by triangle inequality, we can break this notion into two, so that this will be less or equal to n1 minus xn plus n2 minus xn, and this is equal to, by symmetry property under the absolute value, this is equal to xn minus n1, and this is equal to, this is okay. Okay, so by symmetry property, these are the same, and of course this comes down so that we have this. Okay, so from the assumptions we have here, we are given this will be epsilon over 2, because when we say epsilon is arbitrary, if you divide it by 2, epsilon over 2 is also arbitrary. Okay, so from the definition we have earlier, xn minus L1 is less than epsilon over 2, and xn minus L2 is also less than epsilon over 2. When we add this together, this will be epsilon. Okay, so let's summarize what we have done here. So therefore, we have said n1 minus L2 is less than epsilon. Okay, so there is a lemma we have talked about before now that says recall that if x belongs to R, okay, and epsilon is a positive number, so that this condition happens. So then we say if this happens, then s is 0. If this condition happens, then s is 0. So we are recalling this. So here, if you compare this inequality with this, we'll see that they are the same. Okay, by letting x to be equal to n1 minus L2. Okay, so following the notion of this lemma, we see from here that n1 minus L2 is equal to 0. And if the limit are 0, if the difference is 0, Okay, this means that L1 is equal to L2. Okay, and we can say both of them are what? L. Okay, since they are the same, just let us choose a letter for both. Okay, so we will now see that at the beginning we say suppose the sequence has two limits, L1 and L2, and at the end we are able to show that the limits are the same. Okay, so this go against our contradiction. Okay, that is, we cannot have two limits, we can only have one limit. Okay, so we say that this is a contradiction. Hence, the limit of xn, okay, is unique. Okay, as proved here, the limit of xn is unique. Okay, so this is how we prove the uniqueness of limits, and it is a very powerful tool when we are talking about convergent sequence. Okay, if you have a sequence and it converges to a point, such a point will be unique. This is what the theorem is saying, and we have been able to verify that when in our last class, that if you are given any sequence, any convergent sequence, okay, let's say let xn be equal to the sequence 4n over n plus 1. Okay, so n ranges from 1 to n. Okay, so if you look at this sequence, let us evaluate the limit of this sequence. The limit here means the last number of this sequence. Okay, let us evaluate it and see truly whether it is unique or not. Okay, so by direct substitution, one will see that this will be infinity over infinity, which is indeterminate, But by now evaluating this, or by simplifying this, one will see that, and how do you simplify this? We divide each term of this sequence by n, because n has the highest power here. The variable n is the highest power of the sequence. Okay, so if you divide this by n, this will be 4. If you divide this by n, it will be what? 1. And dividing this by n, it will be 3 over n. Okay, so by applying this limit to this, okay, this will be equal to the limit of 4. Since 4 is a constant, it should be 4. Okay, limit of 1 is 1, and the limit of 3 upon n is 0. Okay, so the limit here is 4. Okay, the limit here, as we have said earlier, is unique because 4 is 4. Okay, there is no other representation as 4. Okay, so it's unique. So that is what the theorem is saying. If you have a sequence which converges to a particular point, such a point is unique. So that is that on the uniqueness of limits. If there is any question, let me know in the comment section. If there is none, let us move to properties of convergent sequence. Any question? All right. So let us look at the properties. So anytime we talk about properties of any notion in mathematics, we are referring to the usual operation, that is the multiplication, subtraction, and division. Okay, we want to see how they perform when we are considering okay. So we say let xn, yn, and zn be three convergent sequences say they converge to x, y, and z respectively. And what do we mean by this? What we are saying here is that we are saying that the limit of xn as n goes to infinity is x. Also, the limit of yn as n goes to infinity is y, and the limit of zn as n goes to infinity is z. Okay, so we want to see what happens if we find the result, if we find the addition or the subtraction or multiplication of this convergent sequence. Okay, so and we are going to list this. Number one says the limit of xn plus or minus yn plus or minus zn. If you have a limit for the addition or subtraction of the three sequences, okay, this means that this limit can be distributing from them, and we can have this while preserving the addition and subtraction. Okay, so this can be distributed from them, and of course, this is equal to x plus y plus z. Okay, because each of these converges to limit of xn converges to x, limit of yn converges to y, and limit of this converges to this. Okay, so this holds for both addition and subtraction. Okay, so we can prove this in order using the notion of convergent sequence. Okay, we can also prove this using the notion of convergent sequence. Okay, let's take them. Let's take two at a time. Okay, let's consider. Okay, so I want to see another proof of this. So suppose that xn converges to x. This arrow means xn. This arrow means convergent. Okay, from the word tends to. The first thing we have discussed there is only true for computational purposes. What we are doing is for mathematical analysis purposes. Okay, we want to prove the same thing we have done here. Okay, using the notion of convergence that we have defined earlier. So here we say suppose that xn converges to x and yn converges to y. Okay, don't forget we are using two cases now. We are using both this and this. Okay, So by definition, we say for given epsilon greater than 0, there exists n1 of epsilon and n2 of epsilon. The first n1 of epsilon, okay, goes for the sequence xn, and y that of n2 of epsilon goes to yn. Okay, suppose I'm including, if you are including z there now, okay, we can also have another n of epsilon. That will be n3 of epsilon for z there. But here we are considering just two sequences. Okay, so this means this. So xn minus x is less than epsilon for n greater than n1 of epsilon, and yn minus y is less than epsilon for n greater than n2 of epsilon. Okay. Here we assume that Sn converges to x and y converges to x or to y. If that happens, we can show the definition for convergent. Okay, for each of the sequence. Okay, for xn we have this, and for yn we have this. So according to the law, we want to see whether xn plus yn minus this will also hold. We want to see this. We want to see whether, if you find the difference between this and this, we can have this less than a positive number. Okay, so let's see this. So if we rearrange this, this is going to be xn plus yn minus x minus y. And by grouping, we can have this to be xn minus x plus yn minus y. Okay, and this is less or equal to xn minus x plus yn minus y. So by definition, this is less than epsilon, and this is also less than epsilon. Okay, this is 2 epsilon. When we break this down to this form, we have this. Okay, in summary, what we have got here is that xn plus yn, okay, minus this, okay, is less than 2 epsilon. Okay, since epsilon is arbitrary, okay, you can say 2 epsilon, okay, can be given as epsilon naught. Okay, so you can write this as epsilon naught. Now, since the difference between this is also less than a positive number, okay, just therefore you can say that the addition of these two also converges to this as n goes to infinity. Okay, so this also holds for subtraction. If you change the sign here to negative and sign also to negative, we can also prove that this will be less than a positive number. Okay, so let's state the properties first. Let's state all of them first, and then we take one or two of them and then we prove. So this is for addition and subtraction. It's also for multiplication. So let us state everything. What we are saying here is this. This converges to x plus y plus z. Okay, and let's call this part A, and part B, xn minus yn minus this also converges to x minus y minus z. Okay, as n goes to infinity. Okay, so this is a summary of what we are saying. So 2, okay, is that if we are to multiply, also, this also gives this as n goes to infinity. Okay, so 3 for any scalar alpha. If you multiply alpha to a sequence, okay, this simply means this. Okay, since xn converges to x, if I want to multiply the sequence with a particular scalar alpha, okay, alpha xn will converge to alpha x, also as n goes to infinity. Okay, so 4, this can also hold for two scalars. For example, for any scalars alpha and beta, if you multiply alpha to Sn and beta also goes with Yn, okay, this also means this. Okay, as n goes to infinity. It is also a property. Okay, we can also have the division property. Okay, this says if you have two convergent sequence, okay, and they are related, both of them are related like this. Okay, okay. Initially, you have said Xn converges to X, okay, and Y also converges to this, okay. But this will come with the notion that provided the denominator y is not 0. Provided the denominator y is not 0. Okay, so we still have some of them. Let's consider the power law. And that will be that will be 6. If you have a sequence Xn and it is raised to power k, here you have assumed k is a positive integer. This will also converge to x raised to the power of k as n goes to infinity. Here k is a positive integer. That is, if the sequence has a power, the sequence has a power k, okay, and then we know the sequence will be converge to x, okay. So even with this power, okay, this goes to this. Okay, similarly, if we have the kth root of xn, if you have the kth root of xn, this converges to the kth root of x, okay, as n goes to infinity. Okay, here also k is a positive number. Okay, k is a positive number. So these are some of the properties of our sequences. Okay, and we can as well prove this also holds for example, if you look at property 2 here, you have considered 3 sequences, but it also holds for 2 sequences. Okay. Okay, it's also holds for 2 sequences, and I'll be able to show that this also holds for 2 sequences. Okay, That is, if you have addition of two sequences, if each of them converges to a particular limit, okay, the addition to also converges to the. So let us prove one or two of these. Okay, while we leave the rest as exercise. Okay, so is there any question? So is there any question from the audience? No question. Okay. So let us speak. Okay, let's prove for this. And then maybe this. Okay, this is straightforward anyway. Okay. Proof. Okay, I think the part 2 there. Is it the part 2 or part 1B? Okay, let's look at part 1B. Okay. For two sequences now. Suppose that I think we're talking about subtraction there, right? Suppose that xn converges to x and yn converges to y. Okay. As n goes to infinity. So we want to prove that xn minus yn converges to x minus y. Okay? And we can similarly take this notion to three sequences. Okay? So if xn converges to x and yn converges to y, we want to show that the difference between the two sequences, xn and yn, also converges to this. Okay? So since xn converges to x, earlier on, since xn converges to x, then this means this. So also yn converges to y means that y minus y is also less than epsilon. Okay. Now, since we are considering two sequences in two parts, we can divide this over 2 and divide this over 2. Okay. This doesn't spoil the argument there, since epsilon is arbitrary. So if you divide an arbitrary number by 2 or by any number, okay, the solution is also arbitrary. Are we there? All right. So now we want to show that this converges to this. So what we should understand there is this: when xn converges to x, this means that we can find the difference between these two, and they will be less than a number. Okay. When yn converges to y, we can find the difference between the two, and it's less than a number. Okay. Now, for us to show that the difference here converges to this. Okay. So here we can say let omega n be equal to xn minus yn, and omega to be omega to be what? X minus y. Are we there? So then we want to see whether omega n minus omega will also be less than epsilon. Okay? If this is less than epsilon, then we can now say that this sequence xn minus yn converges to x minus y. Okay? Now this will be equal to, by letting this is this, then this negative is this. Then this omega is x minus y. Okay, so when we open the bracket here, this should be xn minus x, okay, minus x, then minus yn plus x. Okay, by opening the bracket, that is what we have. Okay, so we can now group this into two. Let's take the inequality here. So from here to here, when we group this into two, we have xn minus x, then plus, okay, y minus yn. Okay, this is true, isn't it? We are taking this part with addition here, then taking this to the back, so that we have this. So we are doing this in order to make the breaking comfortable. Okay, so by breaking this now using the triangle inequality, you recall that the triangle inequality is a property under the absolute value, and we have done that earlier. Okay, so we are breaking this into two. We are breaking this into two, so that this will be xn minus x plus y minus yn. Okay, so symmetry property says, I think we can all recall the symmetry property, that if we say the absolute value of x, this is similar to absolute value of minus x, that is symmetry. So what that means is that if we should interchange this, equality was there. Okay, equality was. Then from here we can now say that since this is less than epsilon over 2, this is less than epsilon over 2 from here, and here y minus y is also less than epsilon over 2. Okay, the addition of this will give us epsilon. Okay. So what we have done so far here is this. That is, we have been able to show that omega n minus omega is less than epsilon. So for n greater than n of epsilon. So this means that omega n converges to omega as n goes to infinity. And you recall, what's our omega? Okay. Our omega is this. Okay, so this is what we are proving. You will recall we have letting the omega into the xn minus yn, and this omega also to be y minus x. Okay, so and the interpretation of this is that for computational purposes, the interpretation of this is that if you take the limit of xn and yn, okay, this means x minus y. That is, we have a sequence xn that is already convergent, and we also have a limit of yn that is also convergent. Okay, converges, that of xn converges to x, and that of yn converges to y. Okay, if you now bring the two sequences together and mix them together, okay, with this subtraction, if you take the limit of both of them, it will also give us this. Okay, that's what we are proving here. Okay, we have said this we hold for addition, it's we hold for uh, subtraction as you have it here. It also holds for multiplication. It's also for division. Okay, but that of division, there is an additional condition that the limit at the denominator must not be zero. Okay, and other things there. So let us also prove for multiplication for two cases now. Okay, and after that, okay, the remaining part follows from what we have in the one or two. Okay, so if you have any question regarding this,
Sir, our omega
yeah,
will always be the question we are proving.
no omega here we are only using it to it's not to make it look compatible. I mean look heavy in the face. Okay, we make use of omega so that this will not look big. Okay, and to be able to guide us to make the judgment. Okay, okay, look at this now. Assuming I'm writing all of this inside there, it will make it look big. That's why I'm using omega to represent this. The same omega can be used for another thing again. Okay, let's see for that of the multiplication. So I think we can rub this so that we can start out of the multiplication.
Yes.
Okay, so I think that's number multiplication is number what?
Multiplication.
Two. Okay, so the proof of two. Suppose that xn converges to x and yn converges to y. Okay, so by definition, xn minus x is less than epsilon and yn minus y is also less than epsilon. Okay, here I'll give it divided by 2 because we are proving the two cases. Okay, just like we did earlier. Okay, for n greater than n1 of epsilon and also n greater than n2 of epsilon, respectively. So, what do you want to prove? We want to prove that xn, yn also converges to xy. We want to prove this as n goes to infinity. Okay, so but to prove this, to make it easier, let us make use of the omega n. Let omega n be equal to xn, yn, and then let omega be equal to xy. Okay, so what you are trying to prove now is to say that when we have omega n minus omega, it should be less than epsilon. Once that goes, it means this is valid. Okay, once you are able to prove that this minus this is less than epsilon, okay, it means this is valid. Okay, that is the proving there. Okay, so now let n of epsilon to be the maximum of n1 of epsilon. Since we are having two n of epsilon, okay, you have to choose a single one to prove this. Because after multiplication, this is not a single term. That's why we are doing this here. Okay, so we want to prove Okay, we want to prove that this is less than epsilon. Okay, so by our assumption, this is xn yn. Okay, and this is also what xy. Okay, so we want to introduce a trivial term here. Okay, this trivial term means that okay, we are introducing this. Okay, okay, these are trivial term minus xyn plus xyn is a trivial term. Okay, then we have minus xyn. Okay, so this will allow us to group this into two because yn is common here and here x is common. Okay, since yn is common in the first summand, we say that this is this. Okay, then plus here x is common. Okay, now we can now apply the triangle equality to break this into two. Okay, so what's here? We have two terms. The first term is this, and the second term is this. So separated units. So the triangle equality can easily be applied here, and this will be okay. Okay, so this is what we have. What we bring there. Okay, so you will also recall under the properties of absolute value that if you have two terms, okay, suppose we have AB under the absolute value, okay, you have been able to show under the absolute value that this is this. Okay, so here you see that this yn is related to this by multiplication, so it means you can break them down into two. This x is also related to this by multiplication. We can bring them down into two. Okay, using this property under the absolute value. So, and that will be equality. That will be equality. So from here, we are taking this down here. We are not following the alignment. Okay, from here, this is equal to this. Okay, this is yn. Okay, this is xn minus x, and this is absolute of x, and this is yn minus 1. Okay, now it is now good for us to break this further. You will recall here that we say n converges to y. Okay, that is a theorem that says if a sequence is convergent, that sequence is bounded. That law holds. Okay, we now say since xn is since yn is convergent, then it is bounded. Then we now bring the notion of convergent because of this term here. Okay, because of this term. Okay, so okay, we'll state this after. But what we have here, we are turning it to a particular number n later, so I will state that. But from here, this less than is bringing this to be epsilon over 2 here. This is epsilon over 2. Okay, plus this one is also what? Epsilon over 2. Okay, we will now add the condition that since yn is convergent, then it must be bounded. Then it must be bounded. Okay. Okay. What's the name of the theorem again? By theorem I think we label the theorem 2 point, okay, by theorem 2.4. Okay, so we are bringing that in order to, okay, because of this, and also for whatever value is x here, for whatever value x is here, okay, we are very sure that this x, okay, with the absolute value will be what? Will be positive. Will be positive. Okay. So because of the absolute value. Okay. So let's make the conclusion here. Are we there? Right. So now let's come here. Please look up. Since we are trying to justify a notion here, okay, we can describe this in order to eliminate this. And we know this epsilon is arbitrary. And we must choose the epsilon that will suit our solution. Okay, I think I gave the example in the last video. I did that of the video we did yesterday. Okay, it's there. Okay, so we can choose our epsilon in such a way that it will suit what we have. So we can multiply m to this 2. Okay, here we can multiply absolute value of x to this. Okay, all depends on, we are trying to choose a particular epsilon that will suit our convergent notion here. Okay, so having done that, okay, note this. So it means when we are introducing this we have n, this we have what? This. Are we there? Right. So okay, I think let us interpret everything here so that since yn is convergent, okay, the absolute value of n will be m there. Sorry, the absolute value of yn will be m. Okay, like for this notion here, if yn is convergent, then it must be bounded, meaning this is less or equal to m. Okay, so we can interchange this for this. Okay, meaning this is equal to m. Okay, this is n, and then this is epsilon over 12. Okay, this also we have this over this. Okay, so okay, so here this m will remove m, this absolute value of x will remove absolute value of x. Okay, sorry, and this will be equal to epsilon over 2. Epsilon over 2. When we add that together, here we have epsilon. Are we there? Alright, so let's see what we have done. So that is, we have been able to show that this omega n minus omega is less than this. Okay, for n greater than n of epsilon. Okay, so and what this means is that this implies omega n converges to omega, okay, as n goes to infinity. And you will recall that we have let this omega to be what? Xn, Yn, and this will be what? This. Okay, so that's how we prove this. So we can also extend division to three multiplicative sequences. Okay, and that of division also can be proved using this notion. Okay, so other properties follow from what we have earlier. Yeah. For example, look at the third one where we have scalar. The scalar alpha, where we say this. So it's easy for us to prove this. Okay? It's easy for us to prove this. Okay? You know, since we know that xn minus, I think this is number 3, 4. Okay? Since this happens, since this is less than this, okay? Here we can have that alpha is common here, so we can have this. Then we can break this using the algebral property that says we can break this. Okay, since this is multiplying this, we can break this. Okay, by the something will, and this will be this. Now, under the lemma we discussed earlier, we discussed the lemma that says, let me, if I can call the lemma or the name of the lemma. Can somebody tell me? Open your note and then let me. Lemma 1.7. Yes, there is a corollary after the lemma. You say the corollary. Yes.
X member of number.
Okay.
Epsilon.
So in the lemma, we have that if S is a real number
And epsilon is greater than 0.
and epsilon is a positive number.
Yes. So there is a non-negative number alpha such
Yes.
that
Yes, the non-negative number here. You know, alpha as chosen for any scalar. You mean alpha can be negative. Okay. But here, if you take the absolute value of alpha, it is a non-negative. Okay. Here, alpha is greater than or equal to 0. It's a non-negative term. Okay. The condition further says that if we now have this,
it's great
okay,
less than alpha n.
okay, alpha which is not getting negative, then this. Then the condition says that this what will be 0. Isn't it?
Yes.
Yeah. Now, it means if this is 0, what it means is that the entire something here is going to 0. This is the corollary. Let me know the name of the corollary so that I can. Corollary 1.8. Okay, so by corollary 1.8, you can apply that here. So that means that alpha n minus alpha s is going to 0. Okay, what this means is this. We can transfer this time here. Okay, so that this will be alpha s as in to infinity. Okay, so that's what the lemma is saying there. That the corollary to say. Corollary 1.8. So we can apply corollary 1.8 to prove this, to complete this notion here. So from those online, do you have any question? Reduce to 27. Is there any question from the online? Yes. So that is that of the so we can use this the first three properties to prove other aspects there. Okay, and we want you to take that as exercise. So if there is any issue, okay, you let me know so that we can address that offline. Okay. Okay, so the next thing is the Monotone sequence. Yes, Monotone sequence. Take your time. Like class. So, what do we mean by monotone sequence? So let's have the definition of that. What should we label? The last theorem. So this should be definition 2.6. And we want to define what is
started to be done.
yes, is a continuation, please. So definition 2.6. Okay. Yes. So one of the final monotone sequence, and one of the first conditions is that if you have any two successive terms in a sequence and they satisfy this condition or should, okay, we say such a sequence is monotonic increasing. Okay, so two, we say that the sequence is increasing if xn is more than xn plus 1 for each n in n. Okay, so 3, refer to this as non-decreasing if xn is less or equal to xn plus 1 for each n in n. And then number 4, okay, here we have increasing, decreasing, non-decreasing, then we have non-increasing. So if xn is more than xn plus 1 for each n in n. So in all of this, okay, you see there are order which are preserved throughout. Okay, so for a sequence to be increasing, it must preserve this order throughout for any two successive terms. For the sequence to be decreasing, it must preserve any two successive terms. They must preserve this throughout. Okay, likewise for non-decreasing. Okay, we are separating this from here, okay, because of this equality. So when we say non-decreasing means there is a possibility of equality there, okay, and that's why we are we try to separate them, okay. And then when we say non-increasing, there is possibility of equality in any of the two successive terms, okay. So any sequence which satisfies the above condition or one of the above condition. any sequence which satisfies one of the above conditions is a monotone sequence. So if you have a sequence satisfying any of the above, such a sequence is monotone. Okay? So it means if any of these conditions is not satisfied for any sequences, such a sequence is non-monotone. Okay? So we'll now be given example of each based on the condition we have here. What do you mean by this? What kind of sequence satisfy this? And what kind of sequence will satisfy this? And so on and so forth. So we'll be given one example each. Then before we now see before we now look onto the essence of this monotone sequence. Okay, so example, we start with increasing. So the sequence xn equal to is a monotonic increasing sequence. So let's see why we say that. Why do we say the sequence is the monotonic increasing sequence? Okay, so this is because xn, which is equal to this, okay, we must be able to show that this xn, okay, is less than wherever we see n. No, in the definition we make use of xn less than xn plus 1. Okay, here xn means a function of n, and when we say xn plus 1, okay, means a function of n plus 1. Okay, so here we replace n with n plus 1. That is the meaning. If we replace n with n plus 1, we want to see whether n plus 1, we are replacing with n plus 1, then plus 2. Out of 4, this is what? This. We want to see whether this is true for each n. We want to see whether this is true for each n. Okay, so I think we have got what is there. So let's see now. Now for n equal to 1, when n is 1, I want to see whether this is less than this. Okay, for each n I will choose, we want to see whether that will be true. When n is 1, this will be 3. That will be 1. Okay, from the left hand side there. Okay, that means x1 is equal to 1, and this is less than, when n is 1 here, what is it? Let's see that. When n is 1, this will be 2, this will be 6. When n is 1, this will be what? 3, sorry, 2, 4. That will be 6 over 4. That is what? 3 over 2. And then, of course, when n is 1 here, this means what? S2. 1 is less than 3 over 2. Okay, when n is 1, so this is valid. Let's see again whether it will hold for when n is 2. So when n is 2, S2 here will be equal to 3 over 2. That is, wherever we see n, put 2. Okay, that's exactly 6/4. That is 3/2. So when n is 2 here, this will be 2 plus 1, that's 3. That will be 9. Okay, we have 9 at the numerator. So 5. Okay, so this is 9/5. Okay, and you see that when n is 2 here, this is S3. Okay, so let's see. 3/2 is what? 1.5, isn't it? And what is 9/5? 1.8. 1.8. So 1.5 is less than 1.8. This is also true. So when n is 3, after this we generalize. Okay, when n is 3, we will have S3. Of course, this will be 9/5. When n is 3, this is 3 times 3 over, okay. So when n is 3 here, this will be 4, 12. This is 2, right? That will be 12/2. Okay, of course, this is 1.8 is less than 2. Okay, you know, here we are saying when n is 3, so this is, so also 1.8 is less than 2. Okay, you will now see that this should be true for all n. Okay, it should be true for all n. And what it means is that from this, if I will show some of the few terms of this. Okay, let's see some of the few terms of this sequence. Okay, let's write the conclusion first. Observe that this is true for all n in n. So for all n that we choose, this will be true. And this is the reason why we conclude that this is a monotonic. This is a monotonic increasing sequence. So it should be increasing. This is monotonic increasing sequence. Okay. And let's see some of the few terms of this sequence, and why we are able to say that that is true. Let's see. So also, to see the elements, so the terms that we are picking here are two successive terms, okay, of the sequence. So as we have shown here, the first element here is 1, the next one is 3/2, the next one is 9/5, if I'm correct. Okay, the next one is 2. Okay, the next one is going to be, okay, this is how we do that. Okay, now you observe what will be the limits of this sequence. Okay, this sequence has a limit. The limit is going to be what? 3. That is, if you find the limit as n equals to infinity, it's going to be 3. Okay, so meaning when n is 1, we see that 1 is less than 3/2. 3/2 is less than 5/2. This is this. So this should be less than, up to the last time here. Okay? So the interval of the sequence is between 1 to 3. Okay, 1 and 3 are inclusive. Okay, so the sequence is monotonic inclusive. So the remaining times, no matter what it takes us to get to 3, everything lies here. So it is monotonic increasing. Okay, do you have any question? Okay, so let's see another example. So this first example agree with the first condition, that is monotonic sequence. Okay, So example 2. So the sequence xn equal to okay. Let's see some of the few elements here so that we can conclude immediately. Okay. When n is 1, this is 2. When n is 2, this is 1. When n is 3, this should be 2 over 3. When n is 1 over 2. When n is 5, 2 over 5. Okay. So as this is going to where? 0. Okay. And we can see that. Let me see the screen whether it appears here. So those looking out from okay. So as this is going to 0. Okay. And what we will observe is this. The first element here, which is x1, we see that it is more than s2. Okay, 2 is more than 1. Okay, s2 is more than s3 because 2 over 3 is 0.6666. Okay, 0.666 is also more than s4. Okay, and this is more than this, which is this is 0.5. This is 0.4. Okay, so it's more than, and everything will be going up to okay. So they follow this order, the greater than order. They follow the order until the last term there. Also, you see that the entire interval here is between 0 and 2, but it turns out from the maximum to the minimum. Okay, that's the behavior of the sequence. So it is what? Monotonic decreasing. Okay, so therefore the sequence is monotonic decreasing. Okay, and you see that this follows the condition 2 here. Okay, so let's see another example that agrees with the non-decreasing condition. Let's see that. So if you look at the Fibonacci sequence, okay, you see the Fibonacci sequence. I think we knew that before, but let's recall it. The Fibonacci sequence. The sequence is 1 1, isn't it? 2 3 5 8, okay, 13. Then this goes. Is an example. Is an example of monotonic non-decreasing sequence. Okay, and why do we say that? We see that apart from being less than that in one of the two successive terms, there is equality here. X1 here is equal to X2. Okay, 1 1. And after that, you see that this S2 is less than S3, which is 2. 2 is less than this. Okay, you see that all other one follows the a similar order. Okay, so that's why we say that if the sequence satisfies this condition, okay, it is referred to as monotonic, non-decreasing, and Fibonacci sequence behave exactly the same way. Okay, so there are other examples of sequence that satisfy this condition. Okay, but we are making use of Fibonacci in this case. Okay, so we should be able to provide more. Okay, so now want to see want to see uh, one example of a sequence that satisfies the non-increasing. Okay, and you know the non-increasing has to be this. Okay, this is non-increasing. Okay, so but before we do this, let's use an example of what is practical to get this. Okay, what is practical? Let's use to get this so that one can. So I want to derive the sequence from what is following now. Okay, suppose or let's say two. Okay. Okay. There are two statements here. The first one says two chocolates are sold for 15 naira, and the other thing says you can exchange 3 wrappers for 1 chocolate. Okay. So what we derive the sequence. Okay. If we have or if one has 200 naira. Okay, that is, let us see the sequence if one has 200 naira. Okay, and following this information that two chocolate can be bought for 15 naira. Okay, so at the beginning with 200 naira. Okay, what one to drive here is the sequence. Okay, the question may follow if it is a series that how many chocolates will you get with 200 naira? Okay, it means the sequence you have, add them up. That's the series. You are still going to that. Okay, so we want to see the kind of sequence we will obtain here. Okay, now let's say the first time we do now. Our first attempt with 200 naira. Okay, we are going to obtain how many chocolates? With our first attempt, I'm going now with 200 naira. What will be my first chocolate that I want to get? Okay, so one can say that this is divided by this. Okay,
Like 13 points.
no, how do you do it? This is 2, right?
That's 2.
So let's divide this by this divided by this first.
13 points.
Then you multiply by 2.
26.6.
Remainder.
6.6.
No, we have to do remainder now. Or let's make use of let's think of 300. Okay, so that we can have the exact time. I think with 300, one can get 40 here. Okay, when we times by 2, okay, it means at the beginning, when one goes with 300 naira, the first thing we get is 40. Okay, so let's the sequence be XN, and then the first time is now 40. So what is the remainder that we have? The remainder is 0. Okay, because all of we will use everything there. Now, after consuming 40 chocolates, okay, there will be how many wrappers? 40 wrappers. Isn't it? Now, there is an information that one can exchange 3 wrappers for 1 chocolate. Okay, meaning if I'm going with 40 wrappers, how many chocolates will I get? So that's the second attempt. Okay, that will be, I'll get 13, and there will be many one wrapper. Okay, meaning that one wrapper I can't use it for anything, so that's why it's many. But with 40 wrappers, I can get 13. Okay, now that's the second attempt. So that is 13. Now the third attempt will be, I'm going there with 13 wrappers. Okay, so with 13 wrappers, how many one can obtain? Huh? Okay, 3 wrappers, that will be 4. 4 remainder 1. Okay, with 13 wrappers, one can obtain. So remainder 1 again. Okay, so you know we have not used this. The base is not used, that's why we are not using it. Okay, again, let's go with 4 wrappers and see. So that's the four attempts. The 4 attempts. Oh, if I go with 4 wrappers, I can only get 1 chocolate. Okay, so 4, 1. Okay, this is another 1. The remaining I have is how many? 3. 3 wrappers. Meaning if I go with this remainder, I can get another 1. Okay, so that is the 5th attempt. If I go with that, what will I get? I'll get 1. Okay, so maybe this is 1. So where we are going is this. This is x1. You will see that it's more than the x4. X4 is sorry. This is S2, and S2 is more than what? S4. Okay, S4, X4, and S4 was what? It's called S5. Okay, so meaning I've been able to achieve that Xs is greater than or equal to Sn plus 1. The preceding term is more than the isolated term. So the kind of sequence we are obtaining here is what? Okay, this is what? A non-increasing type. A non-increasing type. You get that? It is because of this equality. Okay, that will make us put equality here instead of saying this, because of this equality, so we can add this to this. Okay, so this is an example of one of the examples of non-increasing sequence. You get that? So now, a question may now further ask that how many chocolates, though we are not under series now, but if the question is asked that how many chocolates you won't get with 300 naira, that's when you now do the addition. Okay, this plus this, that is series, plus this plus this plus this. So we add everything up to get the number of chocolates we can get with 300 naira. Okay, so that is in series.
Now, I'm still confused about this. Where we go with 4 wrappers or
About
this 4 wrappers?
4.
Yes.
Okay, with 13 wrappers.
I understand that 13.
Okay.
I understand that. We have 4. I'm still confused from that.
Okay, we have 13 chocolates. After consumption, you have 13 wrappers. Okay, if you go for the exchange now with 13 wrappers, okay, you are going there with 3 wrappers for 1. Okay, out of 30 now, you can only get 4. Okay, you know that will be 12. That will be 12, right? So you can only get 4. Because what I say 12, so remember 1. Okay, so that's how you do until. So the last one here, now use this three remainders for it to get 1. Okay, so but what we are after here is the sequence, the type of sequence that we can obtain from the exchange. Okay, is a type of non-increasing sequence. Okay, so we should note that after this, note that any sequence that do not that does not satisfy the 4 conditions above is a non-monotone sequence. The 4 conditions we have talked about, I think you can easily get there. Okay, any sequence that does not satisfy the such a sequence is a non-monotone. Okay, let's give an example of non-monotone now. Okay, a sequence that does not follow a particular order. Okay, so we call that example 5. So the fifth one, so the sequence is okay. Let us show some of the few times we can get it. This is minus 1 1, minus 1 1. Okay. Is a non-monotone sequence. Reason? What's the reason? Reason, we see that the first term is less than the second term. Now, the next 2 successive terms, we observe that this is this. Among the definition, do we have anything like this? Okay, we will say again that this sort is also what? So what we are now having is the oscillatory type of sequence. So it's not monotone. Okay, so it's a non-monotone, and there are many sequences that behave this way. Okay, and we also recall that this sequence we are able to say that it is bounded earlier. Now another thing to it is that it is non-monotone. Okay, it is bounded, not convergent. Now it's not a monotone sequence. Do you get that? Now, where we are now going is this. Where we are going is this. Where we are going, okay, is to talk about the converse of theorem 2.4. Theorem 2.4 says, you will recall that theorem 2.4 says every convergent sequence is a bounded sequence. Okay, that is, if this is a statement, I will call it P, and this is a statement, we say it is Q. Okay, P implies this. But earlier on, we have said this does not imply this. That's our argument. Now, we want to introduce a notion to the sequence now. That if this Q is bounded, yes, it's bounded, monotone type. It is bounded and monotone. You get that? Then this Q can be tensed to this. You get that? Already here, we are using the notion of boundedness before. Okay? Now, because it is now bounded monotone, it is no more ordinary Q again. I will give it what? Q star. But the Q has been different from this. Okay? So this is already bounded alone without talking about the monotonicity of it. Now, if it is monotone, okay, its form has changed to Q star. We can now say that the converse can hold. Okay? But we cannot just say this. We have to bring in the form of the theorem. Okay? So how do we now state it? Let's have the next theorem. I think it should be theorem 2.7. Isn't it? Theorem 2.7. Yes. So, and this is how we now define it. Yes. We now define that theorem 2.4 as this. That a monotone sequence is bounded if and only if, note this statement. Okay? Because this statement we are trying to justify here. Okay? Now, let's call this. I started with a monotone sequence bounded. That is the Q star I'm referring to the other time. Okay? We now say it is this, and this can also be this. We are using P before that. P can go to Q, right? But with the addition of monotone, okay, you can say this can also go to this. That is what the theorem is saying. Okay? But the proof now will now be in two phases. Just that one of the phases has been proved in theorem 2.4. Okay? That is the statement that P goes to Q. Okay? It's one of the proof here, but it has been proved in theorem 2.4. Okay? So the proof will be dropped here. Okay? The proof of this will be referred to as theorem 2.4. But a case where Q star now goes to P is what we'll focus on. Okay? We have not proved that before. I think we get that. Okay? So, but originally, the proof is in two phases. Okay? This part that says P goes to Q star has been taken care of earlier on. Okay? So, we won't deal with this. Okay? So, let's take them. I think you still understand the notions, all the notions we have defined earlier in our last section, supremum, infimum, and likes. All right. So let's see the proof now. So now say let Xn be a bounded monotonic sequence. No, if it's monotonic, one has to be specified. Okay, so we are using increasing in this case to prove. We are using increasing, say it is increasing. Okay, if it is decreasing, you can also use that to prove. Okay, but here we are picking one. So let us be bounded monotonic sequence. Okay. So you know if a sequence is bounded, there are two informations here. When the sequence is bounded, okay, and it is increasing, of course that sequence is going to somewhere. It is bounded meaning it has both the minimum and maximum. Now, if the sequence is now increasing, where is it going to stop? Do you get the message? You have a sequence which has a minimum and also has a maximum. If the information now says the sequence is increasing, meaning it's going towards the right, okay, it's going to stop. It's going to stop here. Okay, you now see that this same n, okay, you can refer to it as a supremum of what? Xn. Okay, here we will not use n, but we will use supremum, and we will label it to be what? Alpha. So in another proof, if I want to use decreasing now, the sequence is bounded and it is decreasing. Okay, the sequence is going what? Left. Okay, so when is it going to stop? It's going to stop here. Okay, so this means that if I don't want to use the word minimum here, okay, we'll use the minimum of what? Xn. Okay, and then in this case, just so for the proving sake, we can call the infimum of what? Beta. Okay, but we want to use this part. Since we have said increasing, we want to use this part. Now, let alpha, since I said the sequence is bounded and it is what? Monotonic. Okay, now let alpha be the supremum. Why am I using alpha and supremum? Because I know when it is increasing, it's going definitely to this place. Do you get that? Okay, let alpha be the supremum of Xn. Okay, and what happens if that is the case? What happens? Then Xn will be less or equal to alpha. If alpha is the supremum of that sequence, all the terms of that sequence will be less or equal to alpha. If I pick a term in the sequence, it will be less than alpha. So equality can happen because they can both meet on the boundary. Okay, and this happens for each n. Okay. Okay. Also, since Xn is increasing, okay, there is a term which is greater than n. There is a term which is greater than n, so that Xn will be less or equal to, will be less than Xn, and this will be less or equal to alpha. Am I lying? If you look at the definition of increasing, okay, you will see that this substrate Xn will be less than another substrate, which is more than this. Okay, now we are not choosing n to be this substrate here. Okay, a substrate that is greater than this, okay, we do what? N plus 1, or say n plus 2, but the nearest one is n plus 1. Okay, and that's why we are using that to be m here. Okay, so now for an arbitrary number epsilon greater than 0, for arbitrary number greater than 0, we have that if we should add this epsilon now, so what we are trying to do here is to decision this. I will be using this and this together. Okay, why am I using the term after this? Is because the term here is usually more than this. Okay, and since it holds for this, it must also hold for this. Okay, and by transitivity, I will stick with this. Now I'm trying to using the particular number epsilon now. Okay, if we add epsilon to alpha, no matter how small is epsilon, this alpha will be less than this. No matter how small is epsilon, if I'm adding a number, a quantity of the number to this number will be what? This, since this is positive. Okay. Now, this will also be so not only on the right hand side, it will also satisfy the left hand side too. Okay, and this implies this alpha less than epsilon. Sorry, alpha minus epsilon. Okay, will also be strictly less than xn. I don't want to use this anymore. And why? Because of transitivity. I want to use this and this. Okay, or we can include it later. We will remove it by transitivity. Okay, so we have said this will not only be true for the right hand side inequality, it also be so for the left hand side inequality. When we say remove epsilon from there. Okay, so this will be this, and this will be less or equal to alpha, and this is less than alpha plus e. Are we there? Yes. Now, by transitivity, I don't want to use this anymore. Okay, since this is less than this, okay, and this is less than this, okay, by transitivity I can jettison this, okay, because we only use that to build the theory there. Okay, it's not an end use there. So this implies. So this implies alpha minus epsilon is less than xn less than alpha plus e. Okay. Also, if we remove alpha throughout from this inequality, this will be xn minus alpha. Okay, this. What are we trying to prove? You know, we have assumed that the sequence is bounded and monotone. We want to show that the sequence is what? Convergent. Okay? Then we'll now talk about the unique point of the convergence. So, by definition of absolute value, I think we are seeing the similitude of this under the absolute value. Okay, by definition of or by property of absolute value. So this means something that we have known before, and it's nothing but what? Xn minus alpha less than epsilon. Okay, and this will be so for n greater than n of epsilon. Okay, so we can now conclude this with this. This means that what? This means that the sequence. This means that the sequence xn is what? Convergent. Okay? It's convergent. And what is the point of convergence there? The point of convergence is alpha. Okay? And a question may be asked, why alpha? Because alpha is the supremum. Since it is increasing, to converge to the supremum. So let's have the remark. Okay, we refer to the remark as the remark 2.9. I think the theorem is what? 2.8. Okay, so remark 2.9. 2.7. Okay, so remark 2.8. Okay, what is our remark? We have two observations here based on what we have observed. Okay, if xn is bounded and increasing, okay, then the limit of xn as infinity is alpha. Okay, and this alpha we have said it is the supremum of xn. That is a 1. So 2. If xn is bounded and increasing, then the limit as n goes to infinity, xn will be equal to beta, as we have said earlier. Okay, and what is beta then? Beta is referred to as what? The infimum, okay, of xn. So that is the true remark. Two things we have observed from this theorem. Okay, let me repeat. If a sequence is increasing and bounded, such a sequence converges to its supremum, and we have denoted the supremum by alpha here. Okay, so and also if it is bounded and decreasing, it will converge to its infimum, and we have denoted the infimum by beta. Okay, so that is that on the theorem under the monotone. Here we are trying to relate the monotone sequence with bounded sequence and convergent sequence. How do they relate? Okay, so now if a sequence is bounded, that will be the third part. If a sequence, if Sn is bounded and non-monotonic, from our previous discussions, what will happen? It has no limit. It is divergent. Or you can say it is divergent. Okay? You can say it is what again? It has no limit. Okay? So just know the difference between this. Okay? If the sequence is bounded and increasing, so the sequence will have a limit, and the limit is either the maximum or the supremum. If the sequence is bounded and increasing, then such a sequence will be what? You have a limit which is either the infimum or the. But if it is bounded and it's not monotone, such a sequence is divergent. Okay, please know the difference. Okay, so these are the areas where you are likely to be asked some questions. So if you have any question, those of you online, so let me know in the comment section. Okay, so if there is none, okay, I think it's more honorable for us to stop here. It's more honorable for us to stop here. So in our next class, we'll be talking about Cauchy sequence. That's another notion of sequence, Cauchy sequence. Okay, so we can end the class here. So I say bye for now.